3.9 is the last section of Chapter 3. It's on derivatives of exponential and logarithmic functions. So we'll be learning 4 new rules total, but technically 2 if you think of 2 of them as extensions of 2 of the first ones. So without going into the proof or too much detail about why this is, the derivative of e to the x, so e being that irrational number, 2.718, etc. The derivative of e to the x is actually still e to the x. I think that's the only function whose derivative is itself that I can think of off the top of my head. Okay, so that means for chain rule, if you have e to a function with x in it, it's like saying e to that same function. So we usually use u, or I usually use u, but g of x represents a function. And then you would multiply that derivative by the derivative of u, or in this case, g of x, the function on the inside, which in this case is inside the exponent. Okay, so in our first example, we have u is tangent of 2x. The derivative of tangent is secant squared. This actually has a chain rule in the chain rule. So the derivative of tangent of 2x is secant squared 2x, and then I still need to times the derivative of 2x, which is 2. Okay, so that means when I take the derivative of f of x, it's still e to that u, I guess. So it's really e, let's do this, e to the u. So the derivative would be e to the u times u prime, which is e to the tan of 2x times secant squared 2x times 2. I like to put the 2 in front. And there is my final answer. All right, moving on to our next example, we have a quotient. So we're going to need to use the derivative of y would be low d high. So it's going to be e to this function times the derivative of the inside function minus high d low. So just leave the top there. Derivative of x is 1 all over low low. Okay, let's do some simplifying. So 2x squared e to the x squared minus e to the x squared times 1 all over x squared. If you'd like to factor out an e to the x squared on top, you can. It would just be out in front. You wouldn't be able to cancel anything out though. I'm not able to cancel out like an x squared because it's only in 2 of the terms. It's not in this term. So I'm just going to leave my answer like this. Generally, factored form is not simplified form. Simplified form usually is multiplied out without parentheses. Sometimes we do leave our answer in factored form though, because if we have to do the work to multiply it out, and it's a very big exponent, I've said in the past that it's okay to leave it in factored form, but generally I wouldn't like do additional work to factor it unless there was something I could simplify. All right, our next theorem is on the derivative of a log, in this case, a natural log, or specifically a natural log. So remember, ln means log base e. The derivative of ln of x is 1 over x. So using the chain rule, if I have a function instead of x, so a function inside the natural log, I would do 1 over that function times the derivative of that function. The better way to write it is maybe to write it as g prime of x all over g of x. I'm going to leave it in this form though because we're used to doing like times the u prime. Okay, so in this example, we have natural log of this whole thing. So I'm going to use the chain rule. It's going to be 1 over that whole thing, and then times the derivative of that function, which I am going to rewrite now as a single fraction to put it in simplest form. Okay, let's review some properties of logs, which you would have learned in Algebra 2 and again in pre-calc. The product property of logs says that if I have log base b of m, where m is some expression, added to log base b of n, you are able to multiply m and n together as a single log, still base b. Right now we've been dealing with base e, the natural log, but this is true for any base. Quotient property says that if you subtract logs with the same base, you can combine it into a single log with the first expression divided by the second expression. The power property of logs says that log base b, let's do, m to the n, means that you can bring that exponent in front as a coefficient of the log. This is particularly helpful when we solve equations with logs. This is what we reviewed in chapter 1. Did we do this in chapter 1? Yeah, so if we had like 2 to the x equals 12, you would take the log of both sides and bring down the x. That's the power property. All right, the last thing I want to mention is that when you have a sum or difference inside a log, this does not simplify to anything else, or it doesn't separate. Is in simplest form. So I think we often confuse when logs are added together versus when you have a sum inside a log. So this can't be further simplified. This is as far as you can go. Okay, so using these properties of logs, we are going to take the derivative of this natural log. So what you could do is take the derivative normally, so it would be like 1 over this whole thing, which is another way of just saying you flip the fraction, times the derivative of this whole thing, which would be using quotient rule. But we're going to use the properties of logs to make this a little simpler. So I'm going to first rewrite that function. So I'm not taking the derivative yet. Okay, let's use the property of logs to separate the top from the bottom. So using the quotient property of logs, I can separate this into log of the top minus log of the bottom. Then using product property, I can separate the x squared and the sine of x. I cannot simplify this any further. This is a sum that stays inside the log. Okay. I'm trying to think if I have enough space. Let's write it here. ln of the first term, or the first factor, added to ln of the next factor. And then finally, I can use the power property to bring that 2 down in front. Okay, now I'm going to take the derivative. This is a lot easier to work with because I can just take 3 separate derivatives. So, dy dx of, I'm trying to think of the best way to write this. I feel like I just need to rewrite the problem. Dy dx of this function is going to be, okay, this derivative is 1 over x, and it's going to be multiplied by 2. So I'll write it separate at first, but I am going to combine that. Okay, and then here we have a function inside the natural log, so I'm going to put it under the fraction line and then times by the derivative of sine x, which is cosine x. And then finally, we have this, so that's going to go under the fraction line and then times the derivative of that, which would be 2. And I'm going to simplify this so that the terms that are multiplied together are written as single fractions, which looks cleaner and neater. And this is my derivative. This is my final answer. I kind of want to do it the long way to see if I'd get the same answer. I think it would look very different and it would look a lot messier. I might do that maybe on my own time. Okay, let's do another one. Okay, let's use properties of exponents to rewrite this. So ln, I'm just going to call this f of x so I don't have to rewrite it. ln of f of x. Okay, separate top and the bottom. Okay, on the top, I can separate the x from the square root. On the bottom, when you separate, it's very important that you put this set of parentheses because it's going to, this minus sign is going to be distributed. It applies to everything on the bottom of the fraction line. So you don't want to lose that minus sign. Okay, so there's a product on the bottom, which really means that you're dividing, or yeah, it means that you're dividing by e to the x and by sine cubed of x. So again, the product's on the bottom, but you're really dividing by both those things on the bottom. Okay, so then remember that a square root can be rewritten as an exponent of 1/2. I'm going to write it here, just so I don't have to rewrite it so many times. But if you're listening, hopefully you're following along and understanding what's going on. I'm bringing down the 1/2 in front using the power rule. I'm going to distribute that minus sign, and I'm going to bring down the x. Distribute the minus sign. I'm going to bring down the 3. I believe that's as simplified as I can get. Remember, I can't simplify this sum. ln of e is equal to 1, so I actually don't need to write that anymore. You can if you'd like to. Actually, I take that back. You should probably not, because it simplifies to 1, and in your final answer, you shouldn't have it. So ln of e is 1. This equals 1. All right, let's go ahead and take the derivative now. So the derivative of this function, of ln of this function, okay, so here it is separated. So I'm just going to take each derivative. So ln of x's derivative is 1 over x. This one, it's a 1/2. Let's do this. 1/2 times 1 over 2x plus 1 times the derivative of the inside function, so times 2, minus the derivative of x is 1, minus 3 times 1 over sine of x, and again the derivative of that is cosine of x. Okay, let's simplify. 1 over x plus, these 2's are going to cancel out, so I have 1 over 2x plus 1 minus 1 minus 3 cosine on top and sine x on bottom. By the way, let's actually rewrite this as a single trig function. So cosine of x over sine of x is cotangent. If you leave it as cosine over sine, that is probably fine with me. But it does look a little bit cleaner to just have one trig function. So I'll leave that up to you. All right, great. Today's note taker is a little shorter, so hopefully we'll have some more time to review or discuss any issues, questions we have. Okay, these last two derivatives are extensions of the two derivatives we just learned, e to the x and ln of x, natural log of x. So this is for when the base is not e. It uses a similar idea. So the derivative of b to the x is b to the x times ln of b. So by the way, if this were e to the x, you could technically still use this rule. It would be e to the x times ln of e, which would be 1. So again, e is kind of the unique case for logs and exponentials. I circled those in the wrong order that I said them in. But base e allows you not to have this extra ln of e, so, or ln of b. And similarly, log base b of x is 1 over x, just like ln of x's derivative. But here we will also have an ln of b multiplied on the bottom. Let's write that again. And again, if it were ln, so log base e of x, it would be 1 over x times ln of e, which again would be 1, which is how we get the 1 over x. Okay, let's use these two to solve these last two equations or derivatives. Okay, derivative of h of x. This is going to use quotient rule because we have x's on top and on bottom. So we have low d high. So the derivative of 3 to the x is going to be 3 to the x times ln of 3. Minus high d low. So again, we have that 3 to the x, which we just said the derivative is this. And it's plus 0 because the derivative of 2 is 0. The derivative of a constant is 0, all over the bottom squared. Okay, let's see if I can do any simplifying. So if I distribute this, am I going to be able to simplify anything? I can simplify that. Oh, I can simplify that. Okay, great. Oh, it should be the bottom squared. Low, low. Okay, by the way, this is 3 to the x plus x. That's a property of exponents. You can add them, or 3 to the 2x. But I do have the same thing right here, and this is a minus, so I can simplify this. So my final answer should be, what is that, 2? Oh, it's a 2 times. So it would be 2 times 3 to the x. You cannot multiply that 2 and 3 together. Exponents go before multiplication, so don't try to skip the exponent. It's an x. I can't simplify that. Ln of 3 all over this thing squared. All right, the last one is finding the slope of the tangent at x equals 1. So it's just asking the slope, it's not asking for the equation, and remember, slope is just another way of asking for the derivative, and it tells you the value to plug in. All right, so the derivative of this function is 1 over this function, because it's a function in a function. So 1 over this inside function, but then, okay. And then we need to multiply it by ln of 2. And then we still need to do chain rule, which is to multiply it by the derivative of this inside function. So it's times 3. Okay, and then I need to evaluate at x equals 1. So since this isn't an f of x notation, I can't write f of 1. So I'm going to do that line notation at x equals 1. I don't even need to find the y value here. We should probably do it though. Okay, anyway, is going to be 3 times 1, 3 over 3 times 1, plus 1 ln of 2, which is 3 over 4 ln of 2. Okay, technically this is my answer, but let's find the equation of the tangent line, because I want to remind you how to evaluate logs. So if I wanted to find the y value that corresponds with x equals 1, I would plug 1 into the equation. Okay, log base 2 of 4 without a calculator. You are thinking 2 to what power is going to give you 4? So log base 2 of 4 is 2. So the ordered pair here is 1 comma 2. So my equation here is, this is my slope at x equals 1. This would be my equation. I know that's not what the problem is asking for, but I wanted to remind you of this. All right, let me know if you have questions. I hope you had a nice break. I just realized that I'm filming this on Thanksgiving Day, but you are probably watching it Monday or Tuesday night, so it will have been a while, but I hope you had a nice break, and I will see you in class.